In this video, I'm going to discuss answers and provide some explanations for the worksheet that you just completed on universal gravitation. If you need a copy of the worksheet, I'll post a link in the video description below. Questions number 12, 13, and 14 is going to think about the difference between somebody standing on the Earth's surface and somebody standing on a new planet surface. Let's just call that planet X. And the things we know are the fact that this new planet is twice as large. Well, the radius is 2 times bigger than the Earth's radius, and we're going to assume that the density of each, the density of the planet X and the density of planet Earth, are the same. And ultimately, in 12, 13, and 14, we're going to figure out how big the gravitational force is on this person standing on planet X compared to when they're standing on planet Earth. So the first step in number 12 is just figuring out what is the density of the Earth if we know the Earth's mass and we know its radius. Right? We know the Earth's mass is about 5.97 times 10 to the 24th kilograms, and its radius is 6.37 times 10 to the 6 meters. So in order to figure out its density, remember, density is the mass of an object divided by its volume. So we take the Earth's mass divided by its volume, and the Earth is a sphere. We have to divide by the volume of a sphere, which is 4/3 pi r cubed, r being the radius of the Earth, which is 6.37 times 10 to the 6th. Remember, we've got to cube that radius. Don't forget that. And so we get that the mass, which is 5.97 times 10 to the 24th kilograms, divided by the volume of the Earth, which is 1.08 times 10 to the 21st cubic meters. Take these two things divided by one another, and we get the density of the Earth is a little over 5,000. It's 5,528 kilograms per cubic meter. Question 13 states, if planet X has the same average density of the Earth and a radius twice the size of the Earth, like we just talked about, what is its mass in kilograms? Remember that our density equation, density is equal to the mass of an object divided by its volume. So the density of planet X is equal to its mass divided by its volume. If we rearrange this equation for mass, we get that the mass of planet X is just equal to its density times its volume. And remember, this problem said that we're assuming the density of planet X is the same as that of Earth, which we found to be 5,528 kilograms per cubic meter. So the density of planet X is this. We just need to figure out the volume of planet X, which is based on its radius. So the volume is 4/3 pi, and the radius of planet X is 2 times that of the Earth. And so the radius we plug in for planet X is 2 times 6.37 times 10 to the 6 meters, and we've got to cube that value right there. So the density of planet X, 5,528 kilograms per cubic meter times its volume, which is 8.66 times 10 to the 21st cubic meters, gives us that this planet has a mass of about 4.79 times 10 to the 25th kilograms. Okay? And so now that we know the mass of planet X, now we can ultimately figure out how much gravitational force of attraction exists between this person and this new planet, which now we know has this mass. So that's what we're going to do in number 14. So the gravitational attraction between any two objects is big G times the mass of one object, that's mass of planet X, times the mass of the other object, that's the person's mass. Remember, we've got a mass of 100 kilograms for the person, divided by their separation distance squared, which is the radius of planet X, right? Basically the center of the person to the center of the planet, which is double the Earth's radius, which is 1.274 times 10 to the 7th meters. So plugging all those values in that we found using calculations in number 12 and number 13, we get that the gravitational force of attraction on that person on planet X is almost 2,000 newtons. It's 1,968.4 newtons, which, think about it, it's about double the gravitational force of attraction that they feel on the Earth. A 100-kilogram person is going to feel a gravitational force of attraction near the surface of about 980 newtons, or about 1,000 newtons, and this is about double that. Okay, so a planet that has double the radius, turns out, as long as the density is the same, turns out that the gravitational force of attraction is about 2 times as much. So how much force of attraction exists on a person standing on planet X compared to the Earth? Well, we already know that it's about twice the size. And so when we find our symbolic expression, we should find out that our symbolic expression tells us the same thing. Now let's go through this, just assuming that we have symbols for all these values. ME for the mass of the Earth, rho E for the density of the Earth, mx for the mass of planet X, rx for the radius, and so on. If we want to figure out the size of the gravitational attraction on planet X, we just need to use our universal gravitation equation. So the gravitational force of attraction between the person and the planet is big G times the mass of the planet times the mass of the person divided by the radius of the planet squared, right? The radius of the planet is just twice the Earth's radius, so we can put in 2 times RE. Now, we'd first plug in just mx, but we need to put that in terms of the Earth's mass. So we need to come over here to figure out an expression for the size of the mass of planet X. Well, what's an expression for the size of the mass of Earth? Well, it's the density of the Earth times its volume. We're just using here a density equation. So it's the density of the Earth times the volume. Remember, 4/3 pi r cubed for the volume of a sphere. And so this right here is an expression for the mass of the Earth. For the mass of planet X, it is its density times its volume. It has the same density of the Earth, so we just plug in rho E, and its volume is 4/3 pi times its radius cubed. And its radius is twice the Earth's radius. We plug in 2RE right here. So when we cube this expression right here, we get r cubed and 2 cubed, which is 8. And so when we kind of pull this 8 out, we get that the mass of planet X is 8 times this expression right here, the density of the Earth times 4/3 pi r cubed. And if we look up here, that's the mass of the Earth. And so when we have a radius that's twice the size of a planet, because we're cubing that radius, it makes the mass of that planet 8 times larger. So the mass of planet X is 8 times bigger than the mass of the Earth, which is why we can plug in for the mass of planet X 8 times the mass of the Earth. So now once we have this, we can figure out the size of the gravitational attraction. Now it's kind of like a proportional reasoning question. We have a planet where the mass is 8 times bigger, but you are 2 times farther away from the center of it. So we're doubling R, and we're multiplying the mass of the planet times 8, right? Comparing the mass of X to the Earth. And so if we pull out the 8 in the numerator, we get that. And we've got 2 squared in the denominator. So we've got 8 divided by the square of 2 times big G times the mass of the Earth times the mass of the person divided by the radius of the Earth squared. And this right here is just the gravitational attraction on the Earth. So looking at these coefficients will tell us how much bigger or smaller the gravitational attraction on planet X will be compared to Earth. So it's 8 divided by 4, or just 2. It's 2 times this expression, which is the gravitational attraction on the Earth. And so looking at this symbolically, even without knowing specific values, we can say that the gravitational attraction the person experiences on planet X is 2 times bigger than what they would feel on the Earth.